Hi everyone. In this Connect with Networking video, we're going to discuss Chapter 6, how we design computer networks. Let's go ahead and get started. There are lots of components to a modern network, particularly for medium to large scale businesses. And through the next couple of chapters, we'll be discussing networks at the local layer, we'll be discussing backbone networks, we'll be discussing wide area networks, and we'll be discussing connection to the internet. But for today's lecture, we're going to discuss the overarching principles for how to design a network. The traditional approach to designing a network was a very systematic process that began with an analysis phase where we would meet with the users for our network and determine their needs for specific applications and specific equipment and estimate the amount of data traffic that we would expect on each part of the network. We would then move on to the design phase where we would come up with both the logical and physical networks that we're going to use for our potential solution. And then we would implement that solution, building upon the design phase specifications. The traditional network design does have its advantages. For slowly evolving networks or networks that are static, you can design a network that perfectly fits a particular scenario. However, most modern computer networks don't fall into these categories. Most networks are actually quickly evolving and quickly changing in terms of the kinds of devices that are connecting, the number of devices that are connecting, and how we're using those networks. Because the traditional network design is time-consuming and costly, it's probably not the right approach for most modern networks. We need to be able to respond more quickly. We need to be able to respond to ever-escalating needs of network traffic, and we need to respond to the fact that hardware costs have actually decreased quite a bit, but staff costs have increased over time. So we have different needs and we have to respond differently. As a consequence, many modern networks are now designed using the building block approach. And the idea here is that you come up with a few standard components that you use throughout your network, which allow you to have a simplified design and keep costs low. This does mean that the solutions you come up with for your network are not necessarily the best possible fit. They're a good fit, and we compromise on that good fit versus perfect fit because of the simplification, because of how rapidly we can roll out a solution, and because of the lowered cost. The building block approach is an iterative process where we first work through our needs analysis, trying to understand how we currently use our network and how we think we'll be using our network in the near future. We then come up with a technology design where we examine the possible technologies that could either meet or exceed our needs described in the needs analysis. And then we evaluate those solutions using a cost assessment. In the first step, our needs analysis, we're trying to figure out why the network is needed in the first place. Most businesses do need a computer network, but we have to ask the question, what are we going to do with it? It might be simple things like sharing resources, sharing a printer or sharing a file server. It might be for communication with our colleagues and our customers. It might be how we actually deliver our products if they are electronic, or deliver our services. It's possible that when we look at network needs, our current network is satisfying what we need to accomplish, so we don't need to make any changes. It's possible we just need to do some hardware upgrades. But it is also possible that we need to redesign our network to satisfy our current and future needs. When considering needs analysis, it's important to consider the scope of the problem. Local area networks and backbone networks are typically built with organizational ownership. We are going to own the equipment, we're going to build the network, and we're going to manage the network. Because we're going to own the network, we typically build with excess capacity in mind. We don't want to have to rebuild our network too frequently. So by building excess capacity, we can potentially stretch out the lifetime of the network that we are designing. If we're talking about a wide area network, we're often leasing the equipment and the circuits. We don't own the network. And because of that model, we often design at or near capacity and then slowly increase our capacity as needed by renegotiating our lease with common carriers. So wide area networks are often designed much closer to spec. Local area networks and backbone networks are designed with much excess capacity as we can afford. Part of the needs analysis is coming up with a baseline. This is a metric of how we currently operate so that when we design our new network, we can compare what the improvements might be. Baselines include things like the sequence of our current operations, how long things take to process, what kind of work volumes we're currently dealing with, what our network currently costs, and what our current user and management needs might be inside our network, and how they're being satisfied by our current solution. The other part of the needs analysis is breaking our network into all of the architectural components. So we want to evaluate all aspects of our network, and it is often easiest to work from the outside in. So working with our wide area network first, where we can specify particular solutions and we can lease to those exact specifications, and then move inward towards our backbone networks and our local area networks, where we have more room to design various solutions. Sometimes the geographic scope of the network won't include the entire network structure. Maybe we're only looking at our Wi-Fi network, or maybe we're only looking at redesigning our backbone. So sometimes the geographic scope is narrower. After reviewing the existing network and the expected applications that will use the network, we should be able to identify the hardware and software requirements and identify the protocols we're planning on using. And as we know from some of our earlier chapter discussions, many of the protocols have been standardized, so this isn't as much of a choice anymore. The third step in needs analysis is identifying and assessing network users. Many people that use the network will behave very similarly to one another. They're going to be using the network for common activities like browsing the web, reading email, sharing files. But some users might have very different needs. Perhaps you have some designers that need specific software and more expensive equipment. Perhaps you have researchers that need to collaborate with other researchers at a great distance. So you need to consider what kinds of users you have and how many of each type of user. Ideally, the number of categories of users will be small, 2 or 3. Again, this does mean that you are not accurately reflecting each individual's needs. You are trying to come up with some common principle for a group of users, and the solution you come up with should adequately solve most of their needs, though not necessarily being a perfect fit. The fourth step in needs analysis is to categorize our network requirements. Some things will be mandatory. We absolutely need them in order to function. Some will be just less than mandatory, so desirable. And then some options might be wish list, where we really don't need them. They're not even highly desirable, but if it was something we could easily accomplish, then maybe we would go ahead. The results of the needs analysis would be our logical network design. And this is a simplified diagram and supporting documentation on what our network's eventually going to look like. So in this picture, you can see that our building has 3 floors, and we divided our local area networks into the east and west sides of those floors. 5 of these networks are classified as typical, so they're going to get common solutions. But there's one network on the east side of the second floor that requires higher traffic for whatever reason, and as a consequence, their solution might be a little bit different. You'll note there are no specific details in terms of what the local area networks look like or what the backbone looks like. In this case, we are sketching out our solution and recognizing the various types of users and recognizing the different mandatory applications and wish list applications that we might have, but we're not giving any specific detail to anything. That will happen later. The second step of the building block approach is the technology design. And this is where we come up with the physical network design, which may be one solution or many solutions. And we're going to compare and contrast those solutions in step 3. The technology design includes the clients, the servers, the circuits, and the various network devices that we could potentially use. And that does mean that we need to consider whether we're reusing existing hardware or buying new hardware, or whether we can take current hardware and upgrade it rather than replacing it. When we consider our clients and servers, we would like to break these out into just a few small groups. Typical users would be given the same client hardware and software. In Maze, most instructors have a very similar desktop or laptop computer in their offices because most of us behave very similarly. However, there are a few individuals in the building that have specific needs, and might be classified as advanced. And in their case, they might have a much more sophisticated device that helps with their research needs. Many servers in this building are very similar to one another based upon the application needs that they have, but we might have some advanced servers that are specialized for very particular needs. Ideally, we only have this two-category system of typical and advanced, but you might have 3 or 4 in some cases. As the costs of hardware fall, the typical and advanced categories change. So what might have been an advanced category 5 years ago would be what we consider a typical category today, where we give more and more capabilities to the individuals in our organization, even if that is overkill. Because if you'll remember, at the local area network design level, we are often designing with excess capacity in mind. When we look at our network circuits, what we're considering is their capacity. And what's important to look at when designing circuits is their peak capacity, not just how much they're going to be used on the average, but how much they're going to be used at any given moment in time where there is peak demand. So circuit loading is considering how much data is being transferred across a particular circuit. We would consider average traffic for certain, but we're most interested in peak traffic. Think about the roads in your local town or here in College Station. It's fine if our roads can handle average traffic, but what we're most concerned about is can they handle the very brief rush hour traffic. If they're not designed with the peak traffic in mind, then those particular times of day become a real nightmare for driving. And the same thing would be true in our computer network. If we haven't designed it for our peak traffic, then those particular moments would be particularly uncomfortable for the individuals trying to use our computer network. In this case, precision is probably not a major concern. Network circuits are not particularly expensive. So if we're not sure if we've designed a network with enough bandwidth for peak traffic, we just increase the bandwidth of the network. This is what's called a stair-step approach, where we build in a lot more capacity than necessary. One of the reasons why we want to build in this excess capacity to begin with is because upgrading costs are something like 50 to 80% more expensive than designing higher capacity in the first place. Also, very rarely have you had a user complain that they have too much bandwidth and their network is too fast and too efficient. But you certainly have lots of complaints if the reverse is true. Finally, we have historically seen what's called the turnpike effect, where as you increase the amount of bandwidth available to your users tend to use it up. So if you build a particularly efficient and fast network, users will find a way to use that network and take full advantage of the capacity that you've built for them. Most network designs use up their excess capacity within 3 years. There are a variety of tools that are available for the technology design approach. There are some models which can create diagrams of your existing network and then propose potential changes. There are also design tools that can discover your existing network for those diagrams. There are simulation tools that will allow you to model various network behaviors and see what would happen if you increased bandwidth or added an additional server or changed services or moved devices from one location to another within a building. And these simulations can highlight potential problems and also potential solutions. At the end of the technology design phase, you should have one or more physical network designs that could solve your needs analysis. These multiple designs could highlight different trade-offs between performance and cost. Often a higher performing network is going to be more expensive. It will help highlight the design of our circuits and the various network devices that we will need. And it will suggest the upgrades or new clients and servers that will be required for a particular solution. The documentation we provide at the end of the technology design phase is similar to our needs analysis, but we're filling in some of the details. So here you can see that we are specifying the use of network switches for our local area networks in our building. We have a building switch that controls traffic throughout the building, which then connects to a router, which gives us access to the campus core backbone. And we're even specifying some speeds here. 100 megabit per second switches for the local area network, gigabit switches for the building, and for our special local area network on the east side of the second floor, a gigabit switch. Still no specifications in terms of brands or vendors, but we're getting closer. The third phase is cost assessment, where we take a look at our technology designs and compare and contrast how much they might cost. This is a very complex process because we have to consider many different factors. We're looking at circuit costs, which include cabling and installation. We're looking at our inner networking devices, so various switches and routers with different capabilities. We're looking at the hardware costs of our clients and our servers and our backup power supplies. We're looking at software costs, which include operating systems for clients and servers, application software, and any middleware to bridge the gaps between different systems. We're also considering network management and maintenance costs, which over time have become more and more of the portion of overall costs for network solutions. So we definitely want to take these under consideration. And finally, we're looking at wide area network and internet circuits, which are leased and often not particularly negotiable, but they are part of the solution. Cost assessment often requires some request for proposals, where we specify what we think we need from a technology standpoint, and we ask various vendors to give us their best bid for how they would come up with a solution. Multi-vendor proposals could give us an idea of how we could improve performance even more than we initially anticipated. Maybe less expensive because you could be getting different vendors to bid against one another, but certainly could be more difficult to manage. So in some cases, businesses will only deal with one vendor. If you look around Mays Business School, you'll see that virtually every computer in the building has one brand, and that is on purpose because we have negotiated a very good deal with that company. After working through the various cost assessments and receiving the response to our request for proposals, we then need to sell the proposal to management. Keep in mind that much like other infrastructure, like plumbing or electrical work, management often looks at networking as infrastructure, and as a consequence, it is often a difficult sell to propose an upgrade to the network. You have to make a business case. What would improving the network do for the bottom line for the company? So are we increasing our network speed just because we want to, or does it do something specifically that would give our customer a better experience, that would allow us to sell more product, that would allow us to reduce costs or reduce personnel? We need to know what the new network would do for us from a business perspective. After selling to management, a finalized request for proposal would be sent to the final candidates of vendors. We'd revise our technology design as necessary, and we'd come up with our final business case for the network design. And then we would implement. The implications for the building block approach versus the traditional approach is that because of the rapid lowering of cost of hardware and software and circuits, and the rapidly increasing cost of human resources, a faster response to network design is critical. So the building block approach will never give you the perfect solution, but it will give you a good solution, and it will give you that solution much more quickly. And that is worth a lot in today's environment. As network usage continues to grow, designing networks with excess capacity is less and less expensive, so it makes more and more sense to design with lots of excess capacity when you're redesigning your network, knowing you'll be using it up even faster than you anticipate. That's it for this chapter. Thanks so much for watching. See you next time.